differences of temperature, pressure, and winds globally. So now we're going to explain why we have those differences or the variations in the temperature, pressure, and wind. So let's first take a look at latitude. And this is something we've already gone over and reviewed, but now is the notes for it. So latitude is probably the most important factor when determining temperature. And there's two factors that affect this temperature. The first is the angle of the overhead sun. Now, the equator receives direct insolation. So, and this is due to the sun being directly overhead. However, the poles will receive less quality insolation because it's coming at a very low angle. So, and this is due to the sun being low in the sky. The second factor that affects the temperature is the thickness of the atmosphere. So we have the sun's energy having to pass through much more atmosphere at the poles than at the equator. And this means that more energy is actually going to be lost or reflected. And that's due again to that angle that the sun's insolation or the sun's rays have to come into. So these two factors will affect the temperature, and that's all due because of the latitude. So latitude is extremely important in this case. The second variation, or the reason explaining the variations in these temperatures and pressures, specific heat capacity. Now, specific heat, or heat capacity, is the amount of heat needed to raise the temperature of a body by 1 degree Celsius. So this means that it takes a lot of time for some things and not so much time for other things. So it's just the amount of heat needed to raise that temperature. Now, land heats and cools quicker than water. Imagine yourself at the beach on a summer day. The sand is really hot, whereas the water is fairly cold, and that's because the water is still taking a lot of time to heat up. Now, water heats slowly because it's clear, so the sun's energy can actually penetrate to a great depth. There's nothing for it to kind of absorb into. It actually goes directly through water. And tides and currents will actually distribute heat around the globe. And we're going to see some pictures and talk about that a little bit later. The distance from the sea also influences temperature. So here in Florida where we are, it actually matters that we're on the coast versus if we were inland in the United States. That makes a huge difference in our temperature. So water takes up heat and gives it back much more slowly than land. So in this case, what we are going to see is that the water, again, kind of relates back to that specific heat. It's going to give up its heat. It's going to take in heat slowly than land, much more slowly. In the wintertime, mid-latitude sea air is warmer than land air. And so onshore winds bring heat to coastal lands. This is usually why coastlines in, let's say, in really cold places, let's just talk about in the north, like the northeast of the United States. This is why the coast of the north part of the United States usually doesn't get a lot of snow along the coastline. They do get snow, but it's not a whole lot like the inland sections of the United States do, or the inland sections of the northeast. The winds coming off of that, coming off of the coastal land, or coming off of the coast, is actually bringing a little bit more heat. It's going to be a little bit warmer. Now in the summertime, we get coastal areas that remain cooler. So again, this is why if we're in the northeast, you can feel that temperature difference in the summertime along the coastline. Now think about where we are here in Florida. If we were to compare the temperatures in the summertime, we actually are a little bit cooler than inland. And if we were to compare the temperatures in winter, we would be a little bit warmer than we are inland as well. And it's all because of that onshore winds that are coming off of the Gulf of Mexico. Now, areas that have a coastal influence are called maritime or oceanic. I've heard more maritime than oceanic, but your book did mention oceanic. Now, if we were inland areas are called continental. This comes into play when we talk about differences in the types of air pressure and the types of air masses that come into certain areas. Now, sea currents also must be explained because there's a lot of variations in temperature and pressure because of sea currents. Now, sea currents are caused by the influence of prevailing winds blowing across the ocean. Now, remember, the term prevailing means constant. So these are constant winds blowing across the ocean. Now, we see 5 dominant gyres. Now, gyres are dominant patterns that are roughly circular. And if you take a look at this picture here, we can sort of see 5 of them. We see one in the Pacific right here. We see one in the lower Pacific down here. We see one in the northern and the southern Atlantic, so we see 2, and we have 2 here. And then we actually have one in the Indian Ocean. Now, this picture sort of cuts it off, so half of it's on the left and half of it's on the right-hand side. So you don't forget to, that's definitely one gyre. So we have about 5 of them around the globe. Now, in the northern hemisphere, these gyres actually rotate clockwise, while in the southern hemisphere, they rotate counterclockwise. And this is due to the rotation of the Earth. So if you take a look in the northern hemisphere, notice these kind of things are going clockwise. Our southern hemisphere gyres are going counterclockwise. We also have one that circles Antarctica, and that goes from west to east. There is no comparable one up in the northern sections around the North Pole because of all the land distribution. But around the South Pole, around Antarctica, Antarctica is just basically one big landmass right at the southern pole. So we have this huge current going around there. Now, because of the rotation of the Earth, this causes water to actually push westward. So we have this piling up of water on the western edges of ocean basins. And it's sort of like if you were to slop a bucket back and forth, how you get, sometimes you get that water to kind of slop up one side of the bucket or the other. This is kind of what's happening. We actually see a higher ocean on one side, on the western side, than we do on the eastern side. It's kind of interesting, and that's due to the rotation of the Earth. Now, the effect that sea currents have on temperature depends upon the temperature of the current. As you saw in this past page, and I'll go back just briefly, notice that we have blue currents, these are cold. We have red currents, and these are warm currents. So we have a difference in temperature. Warm currents come from the equator, and they're going to raise the temperature of polar areas. Now, this is with the aid of westerlies, so the westerly winds. Cold currents bring cooler temperatures. You go figure. So warm currents will bring higher temperatures, cold currents will bring lower temperatures. Now, specifically in the Pacific Ocean, we have 2 states that exist. We have warm surface water in the west with cold water in the east. So on the western side of the Pacific, we see warm water, and on the eastern side, we see cold. We also see in the Pacific Ocean warm surface water in the east with cold water in the west. Now, this creates something kind of weird because it creates low pressure systems. Let me go back to the picture so you can sort of see this. So here you can kind of see in the northern Pacific Ocean, we have warm currents in the west and cold in the east, but then we also have, up in the really north, we have colder currents on the west and then warmer currents in the east, kind of all down here. So it's actually, we see this almost a couple different gyres, one big circular one, but we see different gyres going on here. So both of these cause low pressure. Now, as air blows from high to low pressure, there's a movement of water from the colder areas to the warmer areas. And this pushes warm surface water into warm areas and exposes colder, deeper water, and this is actually going to maintain this gyre in the Pacific Ocean. So because of the way that this gyre runs, we have both cold water and warm water on both east and west. It causes a low pressure system, which kind of maintains that balance because it's exposing colder water to the surface. So it's creating this pattern and keeping it going. So sea currents are very important for that temperature changes and pressure changes around the globe as well. Finally, we come to the ocean conveyor belt. Now, this is a picture of sort of what's going on in a big picture. Now, you saw little, like kind of all the little circles, all the little gyres that are going on. But this is really the big ocean conveyor belt that's going on. So we see cold, salty water from the polar regions sink because it's denser into the depths. It's going to move towards the equator. Now, the densest water is found around Antarctica, and due to the amount of salt left in the water after ice is formed, this is why we see the densest water there. It's because there all the salt gets left. The ice that's there is actually fresh water. So lots of salt gets left, and then it's very, very dense water. So that that current will actually come towards the pole or towards the equator, and those surface currents will bring warm water to the North Atlantic from the Indian and Pacific Oceans, and it loses heat in the northern areas. Now, as the water sinks, it's going to reverse convection currents. So we have in this big conveyor belt, think of warm air rising, cold air falling. Same difference, the same thing with water. We have cold water sinking because it has a higher density, probably a higher salt content. And then we have the lesser salt content, warmer water rising towards the top. So it's creating this big global conveyor belt. And this is the big global one. So we have all the polar regions are very cold, bringing water up through the Pacific Ocean. It's going to warm in the Pacific. It's going to come back through the Indian Ocean. It's going to kind of connect with some of that warmer water in the Indian Ocean, come back around Africa, come up through the Atlantic, and it's going to turn cold again, go back towards the equator. So it's going to come up towards the equator, go up towards the poles, come back towards the equator, and then it's just a big circle, just one big conveyor belt. So the North Atlantic is actually warmer than the North Pacific. Now this leads to more evaporation in the North Atlantic. The evaporation is going to leave more salt behind, which makes water denser, which is going to sink. So this is the reason why in the North Atlantic we see this pattern where the warmer water turns into colder water. It's going to sink to depths. Whereas in the Pacific Ocean, it's going to turn into a warmer sort of pattern, and it's going to warm itself up a little bit, and it's going to turn into warmer currents coming out of the Pacific Ocean. So the Northern Atlantic comes into warmer weather. We have our warmer currents up here, so it's going to be a little bit warmer up here because that warm current is coming through. The Pacific Ocean, we have a cold current coming through, so it's not going to be as warm. Now, water will travel back to the North Pacific, and it's going to pick up some water, and it's going to reduce that density. So that's the reason why it's not as salty in the Pacific Ocean, and that's because the salt is sort of picking up more water, I guess you can say. And it's not as evaporated, so we have more water than we do salt in this particular location.